Alright, let's watch Qixuan's IA.
I'm actually getting live stream, bro.
Well, I'm live streaming it on VC.
Wait, what if you live stream it on Lumina V3?
Nah.
Wait, just record it.
I'm recording it.
Live stream it on YouTube. Post it on.
Wait, turn on the light or else you can't see the text.
Wait. Live stream on Lumina V3.
Bro, it's so bad you can't see the text.
Alright, guys. Make the font. Make it. Okay, I'll make it bigger. No, but you guys still need to read like the fine text anyways, though. Alright, so I'm an HL student and I finished my math IA like a month ago. So I'll be presenting like what my IA is. I'll go through some of the math concepts so you guys can get an idea, and I'll answer a few questions at the end if I have time left and I don't have to run down to my band performance. Anyways, so my topic on the IA is using ordinary differential equations to model infectious disease spread. Before I get into the topic, let me just talk a little bit about how I thought of this topic. So this topic, actually modeling infectious disease spread, is like a very common topic, and I saw that with some IA exemplars. So that's like kind of the reason for why I was inspired to do it, but sometimes it's not the best to do a common topic because since a lot of people have already done it, they're going to mark you more harshly. But I decided to do infectious disease spread still, even though it's such a common topic, because of the fact that I've have had a little bit of exposure to some more complex ways of looking at infectious disease spread before. So that's why I picked the topic. The personal connection is honestly not that strong, but all of us were impacted by the pandemic. All of us get sick from time to time, so there's the personal connection for you. And so basically the way that I formatted it, I'm not exactly sure if it's like the standard way to format it, but I started with the introduction and I just talked briefly about the topic in general. So I talked about like infectious diseases and a little bit about like why I chose this topic and my personal connection. Okay, so how many of you have heard of the SIR model? Have you actually? So basically, the most simple model for modeling infectious diseases is with a model called SIR, which the S stands for susceptible, the I stands for infected, and R stands for recovered. So right here, we have all of this is basically just some stuff that I explain about this model and some introductory stuff. But right here, this system of equations is at the core of the SIR model and how the simplest way to model diseases. So we have the susceptible compartment. The susceptible compartment changes based on the infection rate. Why is there an S? Okay, so the way that these equations are formatted, and later on we're going to have a more clear version with derivatives, but right now this is like the non-derivative version. So we have the susceptible population at t plus delta t, where delta t is like a very short amount of time, is equal to negative beta n, which is the infection rate, times S in T, which is the amount of susceptibles before, times the number of infected before. Because if you think about it, right, for a disease to spread, there needs to be people who are susceptible and there needs to be people who are infected. The more susceptible people there are, the more people are going to get infected, and the more infected people there already are, there's more disease in the world that's spreading around. And then plus the initial condition of the susceptible. And the same principle holds true for the infected. So the infected population increases by this term, the yearly amount of people who are infected, minus the recovery rate times the amount of people who are infected. And lastly, the recovery rate is just the recovery rate times the number of people infected. Okay, so now for an SL IA, I would say that if you really look into the SIR model, then that's sufficient. But for the HLIA, we need to go above and beyond the SIR model because it is quite a simple model, and we need to show that we have more of a depth of understanding in math, and we can come up with some of our own original ideas. And so in this last paragraph here, I talk about how there are other models that are developed based on the scenario. So for example, there is the SEIR model, susceptible, exposed, infected, recovered, where there's an exposed stage before somebody becomes an infected individual and can infect other people. We have SRS, where recovered people can become susceptible again, SR vaccinated, SR dead, etc., etc. So this family of models is known as deterministic compartmental models, and these are the general model types that I investigate in my IA overall. And just like as the sentence say, deterministic represents the lack of randomness within the model, so there's no random variables in here, and compartmental means that we're categorizing individuals into different compartments, so susceptible, infected, and recovered. Alright, so now before I dive into like more of my exploration of my IA, I talk about some mathematical concepts. So firstly is differentiation. If you know calculus, great. If you don't, like the simple way to think about differentiation is the slope of a function at a given point. So if you have like a curve, then like you want to find the tangent to the curve, and like if you find the slope of the tangent, then it's like the slope of the curve at that point. Integration is the opposite of differentiation. I kind of explain it here as well. And some of the new concepts, I don't know exactly if you need to explain like what differentiation and integration are because they're in the IB curriculum. But for anything, like any math that is new, you should probably explain it. So here we have the definition of an ordinary differential equation. Consists of a function xt and its derivatives with its generalized form expressed as x dx dt, etc., is equal to 0. So basically, like what this means is that we have an equation which has both terms of like a variable x and also some of its derivatives as well in the same equation. And yeah, and now I also talk about like multivariable functions and multivariable calculus. However, I don't really go into depth because that's not very necessary for this project. All we need to know for multivariable differentiation for my IA is that if you have a function, like let's say, like in the bottom line here, let's say we have a function that is dependent on both the variables x and y. So f of xy is equal to xy plus x plus y. And to find the partial derivative, we can look at either variable. So if we want to find the partial derivative with respect to x, that means we're treating the function f of xy as simply a function of x. And that means we treat the y as a constant. So now, if you know some calculus, you know that if we take the derivative of f of xy with respect to x, then the derivative of xy is like it's essentially a constant times x. So the derivative of that is just going to be the constant itself. So, and then we add the derivative of x, which is equal to 1, and the derivative of y. But since we're treating y as a constant, then it's going to be 0. So that means the partial derivative of the function f of xy is equal to y plus 1. In my IA, I also talk about vectors and matrices. So here we have the definition of a vector. Vector is basically kind of like an ordered list of numbers, if you can think about it. And in a geometric sense, it's like if you have an n-dimensional vector, then it's like basically it's a, how do I describe it? If you've taken physics before, it's basically length with magnitude. Extending the idea of a vector to a rectangular array of numbers, we arrive at the definition of a matrix. And we're going to be using matrix operations, which I talk about following as well. So there's scalar multiplication, which is like really easy. So basically, if you have a scalar, which is just like a normal number, multiplied by a vector or matrix, and you just multiply everything inside of it by that number. There's vector addition, which is also really easy. So if you have two matrices, and you add them together, then you just add like the individual terms with the individual terms. The two matrices that you add together need to be of the same size though. And I talk about subtraction, matrix multiplication. Matrix multiplication is a little bit more complex. so I'm not going to go into too much detail here. I also talk about some like other properties of matrices that I make sure to define, because like even though you might think these are pretty trivial, for example, the associative property where a plus b plus c in brackets is equal to in brackets a plus b plus c, it's just an extra precaution to have when writing your IA to make sure that everything is well defined. I also talk about matrix inverses. So in the inverse operation, the inverse of a matrix is basically like division, but we write it a little bit differently, and it also works differently. So the definition of the inverse matrix of a matrix A is that when you multiply A and its inverse, then it's equal to the identity matrix, which essentially works as like the number 1 inside of matrix multiplication. I also use the determinant of a matrix. So the determinant is a special number from the matrix that you obtain that gives you information about some of the matrices properties. So that's like pretty useful. And then I also talk a little bit about how to find the determinant of a specific type of matrix that we'll use later on in this investigation. And because if you know anything about linear algebra and determinants, there's like a generalized formula for how to find the determinant, but that's not necessary because later on, like I wrote the introduction like after I did all of my math. So I knew that I wouldn't have to find the determinant of a generalized matrix. I also talk about eigenvalue and eigenvector. So essentially what this is that if we have a matrix, you can multiply a matrix by a vector. And when you multiply, you can multiply a square matrix by a vector of like the same length, and then it's going to be equal to a vector of the same length. You can think of it as like a transformation of a vector. And when you multiply this matrix and a specific vector, then sometimes it will be equal to that specific vector times like a random number, a scalar. So this is also a very useful property that is useful later on in my IA. Okay, and now this is like the meat of my investigation and where I do the majority of the insightful math. So here I talk about the SIR model, and I extend the SIR model into a system of ordinary differential equations. So instead of like previously where we had like t plus delta t, we instead just do t plus dt, and then we like eliminate both sides and make it look clean. Also, something else is that I like kind of redefine my variables in this section because it makes more sense for the differential form, but I'm not going to talk about that too much. So here we have the system of equations ds dt, so the derivative of the susceptible population with respect to time, aka the rate of change of the susceptible population over time, is equal to negative beta si, and so on and so forth. And here I pose a few questions that I want to investigate about the SIR model before I delve deeper into some other models. So for example, what is the behavior of an infectious disease at the start of its propagation? Can we find an analytical solution to the SIR model or an approximation? Given its initial conditions, when will a disease spread, and so on? So here I answer these problems. So firstly, I think out of all the math, this one will probably be the easiest to understand here. We want to know like what is the initial growth of the SIR model. So here at the beginning of a disease outbreak, a very small fraction of the population, I0, is infected, and most of the population is susceptible, and there are very few recovered individuals, which means that the transition between infected individuals to recovered individuals is going to be much smaller than the amount of people who become infected. Like, if you think about it logically as well, that makes sense. So here we can make some assumptions. So we assume at around the start of the infection, we have like the susceptible population is around 100%, where I represent 100% as 1, and the recovered is around 0. And now we can approximate the equation for di dt, which is the rate of change for infected individuals, into, so the original is beta si minus beta I, but we can approximate this to beta times 1 because we're assuming that the susceptible population is around 100% at the start of an infection. Because if you think about it, right, if you have like a little bit of infected people and they spread to a little bit more of infected people, the total amount of susceptible people is still around the same. So we can assume that it stays constant as 1 for this entire process. So then, and also the recovered population proportion is very small. So we just assume this as 0, and it's going to be equal to beta I. And now we have a very simple ordinary differential equation, di dt is equal to beta I, which is, we're saying that the rate of change of this function is proportional to like the function itself. So right here, based on our intuition, if we think about it, if the rate of change is equal to the function, what does that sound like? It sounds like the exponential function. It sounds like exponential growth. And if we do a little bit of algebraic manipulation, where we isolate like all of the I terms on one side and we isolate all of the T terms on one side, then we get finally that I is going to be an exponential function that is dependent on time and the infectivity. Lastly, it's important to not forget like what our initial conditions are. So at t is equal to 0, the number of infected individuals is I0, like as we defined earlier. So we have I0 is equal to e to the c, and we can substitute this back into the equation. So in the end, we get that the initial growth of the SIR model of disease spread follows the function I is equal to I0 e to the beta t. Okay, and now next I try and find an analytical solution to the SIR model, but I said here in my IA that I was not able to find an analytical solution, and I'm pretty sure there are no like closed form analytical solutions to the SIR system of ordinary differential equations. So instead, I showed like a bit of an approximation where the recovery rate is a negligible fraction of the population. And here I did some more algebraic, I did some more assumptions and algebraic manipulations. And I got in the end kind of like logistic growth. And that makes sense, right? Because we're saying that essentially everyone is either susceptible or infected, because we're saying like the amount of recovered people is so negligible, then we're essentially saying there's no recovered people. So it would make sense that like at first the disease grows exponentially and then it slows down until it plateaus and everyone's been infected. And then here, this is a really important section for my IA in specific, because here we have the condition for epidemics to spread. Like in what cases will a disease actually spread? And based on, suppose that at the outset of the outbreak, because we're interested, like, let's say COVID-19, right? At the start of COVID-19, there were only a handful of people who were infected. And we were curious to see if it would become a global pandemic or it would die out pretty quickly. So suppose that at the outset of the outbreak, t is equal to 0, the number of susceptible is around 100% of the population. I is equal to I0, so a very small fraction of the population is infected, and R is equal to 0. Nobody has recovered yet. For the disease to spread, the number of infected individuals must be increasing. So therefore, di dt must be larger than 0 initially. So if we look at the equation for di dt, it's going to be equal to beta si minus gamma I. And we can just substitute in like S is S0, I is I0 at the very start, and we want to evaluate this at around when t equals 0, so when the infection first starts. And we want to see if this infection is going to be growing or if it's going to be decreasing. So that's why we put larger than 0, because we want to see if the rate of change is going to be positive or if it's going to be negative. And this is like a very simple inequality to evaluate. We get in the end that we want beta over gamma to be larger than 1. So we want the rate of infection over the rate of recovery to be larger than 1. And this is a very important value. It is known as the basic reproductive number, and it's like very widely used in scientific literature relating to epidemic spread. So I talk about here that the basic reproduction number, R0, is very important, and it's going to be used later in my investigation. All right, now I also want to look at the maximum number of infected individuals at any given time. So at any moment, like what is the maximum amount of people who will be infected? And so here, well, we can do some manipulation, and I use the chain rule of calculus to manipulate the equation and essentially find a closed form solution. So this is the closed form solution. I don't know, it's a bit hard to read. It's a bunch of calculus. I won't explain any further. And then lastly, I talked about the total number of people to be infected, and I reached a conclusion that there is no further way to simplify this equation to get the total number of people to be infected in a closed form. But based on experimentation and based on observation, like observing the equation, we can see that the total number of people to be infected increases when R0 increases, their basic reproductive number. So this is also true for some of the results that we found earlier. For example, the maximum number of infected people at any given time. When R0 increases, then the maximum number of people increases as well. And this is kind of like common sense, right? We're just using math to prove common sense, because the more infectious a disease is, and the harder it is to recover from it, then the more people will be infected at a given time, and the more people overall will be infected. And also something to note as well with the total number of people to be infected. I didn't write this in my IA, but just for you guys' sake. The number of people to be infected isn't 100%, because around the end of a very infectious pandemic, there are going to be so many people who are recovered and cannot be infected or infect others that the recovery rate of the infected people is larger than the infection rate where they infect susceptible people. So there comes a point where 95% of the population is recovered and 5% is still susceptible. So not everyone dies in the apocalypse, is basically what I'm saying. All right, and now after I'm done analyzing my SRR model, I talk about some approaches for general models. And one of the approaches is to look at the stability of a function, but the most important approach is we want to find the basic reproductive number R0 for an infection of any general compartmental model. So we want to develop a generalized method for doing so. And the way we do this is I researched this method called the next generation matrix method. So we have a system of ordinary differential equations, which represents the new more complex model, and then we want to use that information to construct a matrix that will allow us to find the value of the basic reproductive number. And so here I just basically talk about how exactly we do this. I don't know if any of you guys will understand this, so I'll just go over this quickly. But so we want to separate our system of equations into two systems of equations. The first system of equations is represented by the vector f of x. So the vector f of x is a vector of a bunch of ordinary differential equations. And in these ordinary differential equations, we have f of x, fi of x, so any one equation within f of x, the rate of newly infected individuals to compartment I, which means that basically what is the function describing when people get newly infected. And then v of x is basically the vector of functions that describe what is the net transfer of individuals out of compartment I. So for example, if we have the SEIR model, we have susceptible, exposed, infected, and recovered, then the process of going from exposed to infected is going to be in v of x. And the process of going from I to R, infected to recovered, is also going to be v of x. Because that's basically a transfer of states. Whereas f of x is the process of being infected. So that would be the process of going from susceptible to exposed. And then we can define capital F and capital V as the Jacobian matrices of fx and v of x evaluated at the disease-free equilibrium respectively. So the disease-free equilibrium, I forgot to explain the disease-free equilibrium. So the disease-free equilibrium is basically when everyone is susceptible and no one is infected. It's an equilibrium because nothing changes at that point. If there's no disease, nothing can change. Disease-free just means that there's no disease. And we want to find the Jacobian matrices. So what is a Jacobian matrices? Basically, a Jacobian matrix is that we have all of these functions, right? We have all of these functions that are dependent on a bunch of different variables. So for example, remember in our SIR function, I was dependent on S and I. It was dependent on the number of susceptible and the number of infected. So we have all of the different compartments, and we want to take the partial derivatives of each of the functions within the matrix, within the vector f of x, with respect to each of the compartment variables. So this is very abstract to see, so I'll explain it later when we look at it with the SIR model. And then in the end, we want to multiply this matrix F by V inverse. So the inverse of the V matrix And once we multiply it, we want to find the spectral radius, which is the largest eigenvalue of this next generation matrix. And the largest eigenvalue here is then the next basic reproduction number. And so we see that in the SRR model, this is very simple. Because in the SRR model, there's only one infected class, so we only need to consider one system of equations. di over dt is equal to beta si minus gamma I. So beta si is the people who are getting newly infected, so we put that part of the function inside of f of x, and we put gamma I inside of v of x, because it's the transfer from infected to recovered. So if we take, if we want to find the Jacobian, because the only variable we have is I, then we take the partial derivative of this function with respect to I at disease-free equilibrium, which is beta S0. And then we can also take this with respect to I as well, which is just gamma. So now if we multiply f with v negative 1, v inverse is just 1 over gamma. This is very trivial because it's a one-dimensional matrix. And if we multiply them together, it's just going to be equal to a matrix with one term beta S0 over gamma. So then the eigenvalues of this matrix are going to be beta S0 over gamma and 0. And because beta S0 over gamma is positive, it's going to be the largest eigenvalue. So it's going to be the basic reproduction number. Okay, so now I have a section here where I'm saying like, let's build some models. And this is more easy to understand if you look at this visual here. So the model that I built for my IA is that we have a susceptible class that goes into an exposed class that becomes either infected or asymptomatic. So like if you think about COVID, right? Because my IA was based around like respiratory infectious diseases like COVID, influenza, etc. So if you think about COVID, when you get infected first by COVID, you're not going to have symptoms. You're going to be in the exposed stage. And you can either have a pretty severe reaction in the infected stage, or you're going to have like basically no reaction at all in the asymptomatic stage. And regardless, both of these stages can cause other people, other susceptibles to become exposed. And both of them become recovered after some time. I also included natural death and natural birth as well in this model, but it doesn't turn out to be that significant compared to the other parameters. But basically here, I just like define a bunch of my variables and I set up a new system of equations that I'm going to be analyzing. So this is the the deterministic compartmental model that I'll be looking in my IA. And this might have been done before, like on the internet as well, but this is like the originality part of my IA, because so far I've been using mostly results that are either easily proven or results that come from like other sources online. So this is like basically my original work, and I want to use the next generation matrix method to find the basic reproduction number of this system of equations. And that's exactly what I do. So all of these pages, okay, it's not cut out. So all of these pages are basically like showing all of the math that I do to find the eigenvalue of the next generation matrix. The next generation matrix that I find from the system of differential equations. And yeah, so in the end, I get that the basic reproductive number, R0, for the system is based on these variables and parameters. And here I have like a discussion of the results. So for example, we can see that overall R0 is most clearly directly proportional to the term sigma over mu plus sigma. And sigma is the transition rate, or an increase in the natural and birth death rates. Wait, okay, honestly, I kind of forgot what the variable names mean, but you can see the idea, right? So like I obtained this result and I talked a little bit about my result as well. And I wanted to apply this on real world data as well. So I found some estimates online, or like I looked at some sources and came up with my own estimates of what each of the variables, or actually they should better be phrased as parameters, are for each of the three diseases that I was looking for: COVID-19, SARS, and influenza. So here I made a chart of like what I would think the approximate values are, and these are like not accurate by any means. Like I just found like random sources, and I also estimated a bunch of them. But I did say so in my investigation, and like your IA doesn't need to be like super scientifically rigorous as well. So then, like, I plugged all of these values into the equations, and I got the following R0 models. So if we use the SIR model to look at COVID-19, SARS, and influenza, then all three of them are going to be infectious. They're going to outbreak as a pandemic. And if I look at the SR0 model, of course, the model that I built, then we see that COVID-19 and influenza die out, but SARS keeps infecting, which is interesting because that's not. In fact, basically the opposite happens in real life. And basically, I just talk about this, and I also compare it with graphs of real-world data for COVID-19, and also like graphs that I generated using my system of differential equations. Also, Claude Code is very helpful for this.
Bro, open code better.
We have SARS as well. This is real-world data for SARS, and these are the graphs that I generated based on my sphere model. And this is influenza, and these are the graphs I generate. So you can see it's very different, and I discussed like why it's different because, for example, if you look at influenza, there's seasonal spikes. So there's obviously a seasonal component to the infection as well. Yeah, and I just talked about these graphs for a few paragraphs, and in the end, I have an evaluation and conclusion of just summarizing overall what I did in my IA. I talk about the model strength, the model weaknesses, and some extensions that I can have to make my results more accurate and to do even more math on this topic. And lastly, I have my bibliography. All right, that's it for my IA. Sorry, I don't really have time for any questions. I'm sorry, I have to go rush down.
Qixuan.
Okay, so we'll probably have a couple more weeks of math club coming up, and we're hoping to have another